Welcome everybody. This is officially, what did we decide to call it? The Vector Clubhouse podcast. All right, we're going with that, but we're not committed to it, so we might just change it halfway through. We might change it in the third episode, but that's what it's called for now. Welcome back to another episode of the Vector Clubhouse. I've got JP here. I'm Zain. Um, and today we're going to talk about scaling with vector databases. Especially, we're going to talk about quantization, which I think is a magical technique that everybody should be using. And we're also going to be talking about horizontal scaling. JP's been learning about that, so I want to pick his brain and ask him questions about that.
Fabulous. Thanks, Zen. How are you going?
I'm doing well. I'm doing well. I think the first one went well, and let's see how long we can do this thing, right?
Yeah, let's see how long we can go before we just start having massive fights on air. Let's count down
That's
to
for the one-on-ones. That's not for this.
keep that private.
Yeah.
Exactly. Yeah, that sounds good. And so you've been talking and learning a lot about quantization over the last couple of months, right?
Yeah, so it started off, I started chatting with Abdel, who's actually implementing all the quantization techniques within Weaviate. And then I didn't, so the first meeting I had with him, I didn't understand what he was talking about. And then anytime I don't understand something, I've got this like itch in my brain that I need to understand it. So then I just did a deep dive on, at that point, very first technique we implemented in Weaviate was product quantization. So I did a deep dive on product quantization, and since then, we're now implementing our fourth quantization technique. And there's now a zoo of techniques. So one thing that I thought would be interesting for people to understand is when to use quantization, where it works, where it doesn't work. Um, like just some of the pros and cons of different quantization techniques.
Fabulous. Yeah,
Yeah.
that sounds good. And obviously I've been asking you a fair bit about it through various like docs and whatever else reasons too. Um, I guess maybe we can start off with like what is quantization because it's a big word. So how would you define it?
Yeah. So basically, quantization, Etienne gave a talk and he had a really interesting explanation of quantization. He basically said if you have a signal, right, and the signal is infinitely precise, you can keep on zooming into the signal and you'll get more and more information. Quantization basically says I don't have enough memory to represent an infinitely precise signal, so you can't just keep on zooming in and getting more details about it. What you have to do is quantize it, right? You have to pick kind of the levels on which you're going to define it. So if you zoom in enough, you won't actually see a continuous curve. You'll start to see these kind of steps and ladders, these quantized bits of signal. Um, and the cool thing about that is that because when you start to quantize and take like steps of this function, it requires less memory to store. Um, and so when we talk about quantization in the context of vectors and vector dimensions, we're basically saying how can we reduce the amount of memory that every dimension of a vector, maybe 1,000 dimensional vector, how every dimension of that vector, uh, how can it take up less memory without us giving up a proportional amount of the information stored in that dimension? So an ideal trade-off would be we want to squish the size that a dimension takes up by 99%, but still retain 99% of the information that that dimension retains. And that turns out to be very difficult to do. So there's always a trade-off of how much are you reducing the size of a vector versus how much information are you actually losing. And so all of this entire zoo of techniques propose different kind of techniques to quantize your vector, squish it, while still retaining its meanings.
Yeah, I really like that Etienne explanation as well, because the idea, I guess, is to really reduce the precision of individual. I don't want to say downsample because it's not the same thing. Like precision of each record, at a time at each point in time, in terms of the signal he was showing. So, from a vector perspective, instead of having, let's say, 1,500 or so of very high precision, let's say floating point numbers, we might just have smaller precision, which was rougher in how many different things it can represent, but is that enough information? I guess it's the trade-off of how much space or how much memory we take up for each dimension of that vector versus the amount of information and the kind of distinguishing different
Yeah.
bits of semantic meaning in that.
Yeah.
So yeah, it's really cool in like concept, and I guess from a deep learning perspective, people might have heard of it if they're a data scientist. In terms of quantizing models, right? But this
Yeah.
is like we're talking about quantizing the outputs, which in our case are the embeddings.
Exactly. So it's interesting that you bring up the quantizing models portion. I I don't think this was a paper, but I found this thread on Reddit last week where they were talking about quantizing Llama 3 versus Llama 2 and some of the older open source models. And they found this really interesting thing. Maybe we can talk about it later, but it goes back to what does it mean to quantize? Um, you're basically saying now there's less steps on this ladder to differentiate between different floating point accuracies, right? You might have had a ladder of like 2,000 steps, but now you've only got a ladder of 20 steps. So now there's not that many indistinguishable pieces, and
Mm.
so it's harder to differentiate. And yeah, you because especially for Llama 3, which is kind of funny, it's a 70 billion model that performs at GPT-4 level. They found that if you quantize the weights, it loses more performance, meaning that it's using more of that accuracy within each weight to do something more magical. Whereas Llama 2 wasn't doing that, so if you got rid of it, it said it didn't have a problem with it, which is very interesting.
That is super interesting. So hopefully that's kind of like enough background on what quantization is at a high level. As you're talking about the steps, I was thinking about studying sort of part time, and so if I said oh here's my grade out of 100,
Yeah,
and then if I just said did you pass or fail, I guess that'll be like a form of quantization, right? Because it's going from a 0 to 100 grade to just like A B
exactly.
or pass fail.
Exactly. So you would pick. So if you think about if you, I like that example because if you uh, kind of go in more detail, you would in order to do that quantization, what would you have to ask? What is the passing mark, right? Maybe 50% is the passing mark, and then that becomes your threshold, and you've basically just described binary quantization, right? Did you pass or did you fail? You have a pass or a fail. You have a one or a zero, and that's exactly what happens in BQ, right? Binary quantization. Um, yeah,
Yeah, and that's really cool. And I guess we'll get into that because I'm still amazed that it worked. I think I mentioned this every time someone
yeah,
mentions BQ. But I don't know if you ever thought on which type of quantization you want to talk about at all, because
yeah.
there's a few different types as you mentioned.
Yeah, so currently, I think we're on the fourth different type of implementation within Weaviate. Maybe I can list them all out, and then we can pick and choose which one. So the very first one that we implemented, this was sometime last year, was product quantization, and then at in Croatia in the company trip, Abdel told me about binary quantization, which, as you mentioned, I can't believe it still works. Um, in the last blog that Abdel and I wrote, I kind of went into why it works, and it's exciting. Maybe we can talk about that as well. Um, then we were looking at scalar quantization, right? Where instead of taking a dimension and squishing it down to one bit, you allow for more steps on that ladder. So maybe you only squish it down to 8 bits. Um, and then the newest one that we're looking at right now is the locally adaptive quantization, the LAQ. So those are the four that we're looking at, and I'm sure that there's more coming. Um, Matryoshka is another type of quantization that has to be done on the model level. Maybe we can even talk about that. That's also super exciting. OpenAI started using it. This paper was actually a couple of years old. OpenAI started using it, and now Google released their own Matryoshka vectors as well. So I think it's becoming really mainstream.
That's awesome. And like you said, this space moves so fast. It's pretty wild. I'm actually going to throw something at you because it just occurred to me that we can maybe have use some visual aids as you talk about some of these. So I'm going to share screens. Hopefully, you can
Let
see
me add
this.
to
So,
stage. Okay.
and then, so this is something we've put together for the Weaviate Academy section on compression or quantization. So maybe this is a good segue potentially to talk about PQ. What do you think?
Awesome. So PQ is really interesting. It's probably Yeah, it's probably the most complicated out of all of them, actually. So this was the one that we first implemented, and I had no idea how this worked. So how PQ works is, um, imagine you've got every dimension on the left-hand side. So you've got this, let's call L 1,000 dimensional vector. Every dimension is given 32 bits, right? 4 bytes to represent whatever useful information that it wants to represent. What PQ says is take the first four of these dimensions, and that's an arbitrary number. You could take the first 10 or the first four, but that's your segment size. And now it says across all of the vectors that you want to store, it could be a million, 10 million, a billion, whatever. You always take those first four chunks and you learn wherever they are in vector space on average. And you learn a centroid for where the first four segments or the first 10 segments are. And that centroid also has a coordinate, right? And so once you found that out, you can store the location of that centroid in memory, and you can just assign a number to it. And that number becomes a centroid ID. Now, anytime you get a new vector, you cut up the first four pieces, and you say, instead of storing these first four pieces, these dimensions, I'm just going to replace it with centroid ID 589, right? And that then allows you to kind of compress the amount of stuff that you have to store in memory. And you do this for all of the different segments one by one. So what you're doing is you're basically taking these different chunks of the vector, and you're learning a representation, you're clustering it. For people that are interested, you just use k-means clustering to cluster the first four dimensions. You learn a centroid for that. Then you do the next four, you learn a centroid for that. And then you have this code book that allows you to map from vector to the centroid. So if you get a new arbitrary vector, you cut it up and you say, okay, I'm going to go to my code book. The first four, the first four dimensions of this vector live somewhere here in vector space. And this is the closest to this centroid ID. So now I'm just going to replace it with that centroid ID. Um, that's pretty much just how PQ works. The reason why this is, I guess, one of the more complicated ones is because there's so many moving variables, right? You can choose an arbitrary segment length. You can choose an arbitrary number of centroids. Um, if you have a very low number of segments, um, you can pick less clusters, but the more kind of the more detailed the distribution of your data becomes, uh, the more clusters you want there to be. Otherwise, you're just going to be summarizing data and
Mm.
losing too much information.
Yeah, it's one of those algorithms where there are a lot of choices, like there's a lot of flexibility
Yeah,
from a user perspective, which is a dual-edged sword.
yeah,
Because if you obviously get more fine-grained control, but it can be a little bit complex. I mean, but if you're using it in Weaviate, I think the defaults are obviously quite sensible. We chose them as defaults because we think they're quite sensible. What I really like about when you explained it to me and also on your blog is that I think you were using like a map analogy
yeah.
where you're replacing individual addresses with things like I think maybe postcodes was the analogy you used.
Yeah, so the interesting thing about this is depending on how far you zoom out,
Yes.
you can say, if I tell you where the party is and I tell you exactly the house, no matter where you are in the world, you can locate it exactly, right? You can tell what country it's in, what city it's in, what neighborhood, what house. And then you can say, okay, I'm going to quantize it a little bit. So now I'm only going to tell you what city it's in. um, you've lost information. You no longer know where the party is, but you know generally where the party is. And then you can quantize even further. I could tell you where if I really don't want you to show up to the party, I could just tell you what country it's in, right? So now you require less memory to remember, but now you can't exactly locate it.
Yeah, it's weird. Whenever I ask you where you're at, you're just like, "Oh yeah, on Earth," and I'm like, "Okay, fine. I guess I won't show up where you are." Um, that's fine. I'm not offended. Um, and that's a cool like that's I think that's a really good analogy because you get to choose how fine grained, like how to represent that information. And the thing that took me forever to realize is that compressing the information in PQ happens in two ways, right? Like one is, as you said, reducing the individual dimensions to sets of dimensions, or called segments, right? So in the example that we show, 4 of these dimensions become one segment or one number. And then the other part is that the original numbers are floating point numbers. But when we compress it, because we're looking for these centroid or some way of representing those numbers, one of, in this case, 8-bit integers, but what it can be, again, whatever precision you want. So I think it's really cool that there's like these 2 different ways of compressing information. And the way we're doing that is, yes, they could be, these hundreds of houses in this area, but hey, let's just represent that with this one postcode, because that captures enough information for us to be able to find the neighborhood, because that's all we're really looking to do here. Well, in the quantized information, we're just looking to say what area are we talking about, as opposed to looking for this specific house where Zen's having a party.
Yeah, exactly. And
Yeah.
so the interesting thing about this is that um, vector space is weird, because in order to tell if you have 2 very different vectors, you don't really need to know exactly where they are to know that they're far apart. It's good enough to just say, this vector is all the way in this neighborhood, and this other vector is all the way in this neighborhood. And because these neighborhoods are on opposite sides of the city, they're pretty far away. It's only when you get to very similar things where you lose information, right? Where the lines are blurred, where if you have a vector that's sitting here and another vector that's sitting here, instead of being able to say that the distance between these 2 vectors is 0.289, now you just say, okay, the distance is 0 because they're squished to the same centroid ID.
Yeah. And it's just occurred to me that maybe we haven't talked a lot about why someone might want to compress or quantize these vectors. And to me, that's like, I guess, a question is like what's in it for the user? Because you're obviously losing information. So why might we want to do that? And I guess the primary reason is to save the amount of memory that's required to hold these the vector index, basically.
Yeah.
Yeah, and for those, I guess, who are like newer to vector databases, the way that these databases work is that they have a thing called the vector index, right? Which is the data structure, or I guess data structure to help you perform vector searches at speed. And the reason that quantization is important is a lot of these indexes are held in memory, not on disk. So having millions or hundreds of millions of these vectors, you kind of pretty quickly start running into scalability challenges if you have tons and tons of these vectors and they all take up a certain amount of space. So then you start having to pay for more RAM, and RAM is relatively expensive. So being able to quantize these vectors means you don't have to pay for as much for your hardware resources. And of course, that means you can grow your database at efficiently.
Yeah.
So yeah, it's a really cool technique. And I guess like theoretically, you can get a huge decrease in vector size just with PQ.
The thing I like about PQ most is that, like you mentioned, it has probably the most configurable parameters, but it's also the most kind of versatile. If you When we wrote initially about PQ, we released a benchmarker. So we released a benchmarker, and the idea there was, if you're using PQ, you could configure it and you could run benchmarks to see what amount of compression you could kind of squeeze out without deterring or without reducing recall. Right? So every time you have one of these techniques, there's a trade-off. And in the case of quantization, it's how much space are you saving, how much cost are you reducing by squishing the vectors, versus how much recall are you actually giving up.
Yeah. And I guess we can maybe talk about rescoring a little bit too, because that was a big part of it, wasn't it?
Yeah.
Getting those good scores.
Yeah.
Yeah.
Go ahead.
No, I was going to just ask you my understanding. So this is what like I like about this, which is that I can have a go at having a hacky explanation for things, and then you can fix it. So my understanding of rescoring is that basically, because we are losing information when we apply compression to these vectors, is that, hey, let's say that we've lost amount of information, but that's okay. So because if we want to get, say, 20 top 20 results, we'll just get a few more. So that might be like 40 results or 60 results or whatever. And the top 20 results are probably in there,
Yeah.
right? And then what we'll do is to get the actual uncompressed vectors
Yeah.
and rank them in the order that they should have been if we were using uncompressed vectors. Is that about right?
Yeah, yeah, exactly. So the analogy that I like to use here is one that Connor and Erica had. They used it for re-ranking, but I think it applies really well
Mm.
for overfetching and then rescoring as well, right? So let's say you're fishing, and I tell you that you have to catch this really rare fish, right? Um, and I don't tell you exactly where that rare fish is. I just tell you the kind of the region that it's in. So if you were to kind of fish and get one fish at a time, it would be very difficult, right? So if I told you, you can fish 5 times, and if you don't get the fish, then you lose the game. It would be very hard for you to tell because you have this huge region where the rare fish could be. Instead, what you want to do is throw a huge net, get like 50 fish, and because you know where the general region it's in, you could get those 50 fish, and then you could examine them and say, okay, this is the rare fish, and then you could let the other ones go, right? So this idea of overfetching is basically the same thing. If the user asks you for the top 5 closest vectors to or objects to a query object, you don't just get the top 5, you maybe get the top 50 or the top 100. So you throw a big wide net, and then when you get those 100, you look at them, you replace them with the actual unquantized vectors, and then you rescore them based on the query, um, and you say which one is actually the closest and which one is the farthest away, and now you can keep the top 5 out of those rescored vectors. So this is initially when we tried PQ. Abdel mentioned that it wasn't working well. Then we applied this rescoring technique, and it was like magic. We would get recalls that were pretty much at the level of unquantized vectors, non-compressed vectors, and you would get all the benefits of the memory savings of quantization as well. So it's pretty amazing.
That's great. And I guess that's the trick in the compression is like you only lose enough information so that the top results are kind of there or thereabouts, right? So that because if they were distributed like everywhere in your search results, the rescoring wouldn't work because the top results would be somewhere like too far away.
Yeah,
But if they're sufficiently towards the top, then you can just overfetch a little bit and then make up for the slight result loss in accuracy by rescoring them with the full vectors. That's really cool. Do you want to get on to the super what I I can't believe it works method, the BQ method?
yes. So BQ is uh, to understand BQ in terms of PQ. Basically, what you're saying is instead of having like a segment that's arbitrary in length, like four dimensions, another four, and another four, you just say I'm going to look at one dimension at a time. And the really interesting thing that I'm going to do now is just look at whether the number at that dimension is positive or negative. Right? So if you look at one of your vectors and the first number is 25, you replace that with a 1. If the next number is -5, you replace that with a 0. You just do that down the dimensions of every single vector, and now you've got this huge vector of ones and zeros. So it's a binary vector, um, and you lose all of this information because now you're replacing potentially 32 bits, 4 bytes, with 1 bit, literally a 0 or a 1. Um, and this works pretty well. Like, it's amazing that you can throw out all of this information and just retain a 0 and a 1 per dimension. And it still works well when you're trying to say, is this vector close to this other vector? Um, so this was pretty interesting the first time I learned about it, which was back in October when Abdel was exploring this at the company trip. And then we had more talks about why does this even work, right? So the magic, the special sauce, is in the fact that imagine you only had a two-dimensional vector, right? So you've got one number and then another number. If you were to binarize this, how many unique kind of combinations would you have? Well, this thing could be a 1 or a 0, so those are two unique combinations. This other thing could be a 1 or a 0, so those are two other unique combinations, right? So 2 times 2, you've got a total of 4 unique potential vectors. It doesn't matter what you want to represent. You only have 4 different unique vectors to represent it with, which is not a lot. Right? But now, let's say you increase it to 3 dimensions. Well, now you've got 3 to the power of 2 unique vectors that you can capture, right? Because you can go and modify this to a 1, 1 or a 0, 1 or a 0, 1 or a 0. And if you look at the different combinations of all of these different dimensions when put together, you've got 9 different possible unique vectors, right? 0, 0, 0, 0, 0, 1, 0, 1,
Two,
1.
two to the power 3, I think. So 8. But yeah, I think.
Oh, yes, sorry.
Yeah.
2 to the power 3. So if you keep on doing this, if you keep on increasing the dimensionality of the vectors, you get this exponential growth in unique distinguishable vectors. So usually, probably the smallest dimension vector that people are working with is 768, right? Um, there's not that many 300 dimensional vectors anymore, and people are kind of pushing how big how big the dimensionalities of these vectors are, right? From 1,000 to now 4,000. The new OpenAI vectors are 3,000 dimensional, and so even with getting rid of all this information, you still have distinguishable vectors. Because in order for a vector to be exactly the same as another vector and you to not be able to tell the difference between them, 1,000 or 3,000 or however many dimensions there are have to be exactly the same. Um, and so this is the unique aspect of why BQ works. When I was trying to understand why BQ works, I understood it from the perspective of like imagine every dimension is a street, and the signal tells you whether you have to go left or right, and you've got 1,000 dimensions, and you just keep walking down, and then eventually you hit another street, and you could choose to go left or right depending on the dimension, and surprisingly, that's good enough to tell the difference between how far apart these vectors are, especially at the higher dimensionality.
Yeah, I think that's a really good explanation of how these vectors work, in that as you increase the number of dimensions, you increase the number, like you increase the information space, basically, so that if you have the computer science folks among us would, know that 32 bits is like 4 million or something like that. So if you have vectors of 32 dimensions, it means you can represent 4 million different meanings. If you have 300 vectors, it'll be that roughly to the power of 10. I don't even know what that number is, something with huge number of zeros at the end of it. And then if you have 1,000 of those vectors, it'll be 2 to the power of 30 to the power of 30-ish. So that's an absolutely humongous
Yeah,
set of numbers. I guess one important thing which you mentioned before to me is that the the embedding model would have to be set up to do this, right? Because you mentioned earlier that if you had 2 dimensions and you're applying BQ over them, that wouldn't be so effective. So for this to work well, I would think each dimension, the more distributed meaning is across each of these dimensions,
yeah,
the better this would work, right? Because if most of your meaning was buried in let's say within the first few dimensions, by varying the actual number, BQ would drop all of that information.
yeah,
Whereas if a lot of the meaning was distributed across individual dimensions equally, that this would work better. That's kind of how I
yeah.
understand that.
Exactly. And the good thing about how these representations or these vectors are learned is that outside of matryoshka vectors, there's not really anything that says the first dimension has to be twice as important as the second dimension, or even more extreme case, the first dimension has to encode all of the meaning. The rest of the dimensions are just random numbers, right? If that was the case, then these quantization techniques would just fall apart because they're squishing every dimension equally, right? And you would be squishing the first dimension, which had all the information, equally to all the other dimensions, which have random numbers in this kind of imaginary vector. So it's a good thing that if you just train a neural network, the variability across all dimensions is pretty much equal, and you can use the variance of a dimension to as a proxy of how much information it captured. Right. So I looked at some of the old OpenAI vectors, and they're about I think they're 1500 dimensional. So I looked at the variance for every dimension, and it turns out to be pretty much the same. Depending on your data set, you might get a particular dimension being higher in variance, but on average, it's the same, right? And so when you quantize, you don't really have to pay attention to the fact that whether you're quantizing the 57th dimension or the second dimension, you just kind of apply your same algorithm to squish it, right? Where this assumption breaks down is in the case of matryoshka vectors, right? Where you train the neural network to you give it more brownie points if it stores information in the first 500 dimensions or the first 30 dimensions or whatever. That's also a choice that you have to make, as opposed to the next 30 dimensions, the next 500 dimensions, the next 500. Now, I was talking to Abdel about this. If you were to take MRL vectors, which in a way are quantizing information because they're choosing to store it in the first X dimensions, and then less information is stored in the next X dimensions. If you were to then squish an MRL vector with like binary quantization or something like that, I I don't know. I haven't seen experiments on this, but I would imagine that BQing or peak product quantizing a MRL vector would turn out worse than taking a normal vector where information is equally spread out across all the dimensions, and then just applying this kind of dimension agnostic quantization squishing technique, right?
Yeah,
And yeah,
that'll be interesting because I guess I don't know with the Matryoshka embeddings whether I think what's the smallest, like 128, are you supposed to go down to if you're truncating them, or is it 512 or something?
I think yeah. So they mentioned that you shouldn't go down. Like I think they tried 32 or even
Oh
64 in
wow.
the paper, and then they mentioned that if you go below this, now you're trying to store too much information in too little dimensions. So now
Mm,
it won't work out. But they
right.
did try up to like 128, and it was fine. And even
Yeah.
the new OpenAI vectors, the chunks that they're cutting it off on are like 512, um, 1020, 1026, um, and then 1536, and then they have one big chunk all the way up to 3000 after.
Right. Yeah, and I guess it'll depend on within those, let's say 512, in the case of the OpenAI ones, how distributed the meaning is within those 512. Like if it's a sliding scale where the first dimension is like a bulk of the meaning or whatever, and
Yeah,
I think we talked about like a similarity to something like a PCA algorithm last time.
yeah,
Whether it's like that or the first 512 have kind of similar distribution of I want to say significance, but not in a
yeah,
statistical sense, but in a more kind of linguistic sense of meaning across those, then the using BQ on those dimensions would you would think work well-ish.
yeah. So when I looked at uh, the MRL vectors from OpenAI, it was almost like a step function, right?
Mm,
The first 512 had a step of significance, and then when you get to from 512 um, to 1024, they had a lower step, but they were all equal, right? So you couldn't say that the 600th dimension was more important than the 700th dimension. They were all equal. But you could say that the second dimension was way more important than the 700th dimension. So you had like steps of importance, and then when you hit a threshold, it would go down, and then it would go down. So um, it was almost like this step function of
that
importance.
makes sense. And I guess that sort of brings about the point of if you're thinking about using BQ, you should, use models that have been tested for it, or some of them I think perhaps are trained to be used with BQ as
Yeah,
well. So I think that would be a big point of consideration if you're using BQ. I just like the idea of using BQ and recommending it to users because I guess as long as you've chosen the right model, you really can't go too wrong with it. Do you know what I mean? Like you just
yeah,
turn it on, and then
yeah.
you're good.
Yeah, I like so when we were talking about PQ, I mentioned that it's got the most bells and whistles. You pick and choose everything. You can kind of benchmark your data, and you can get the perfect settings of PQ. BQ is like kind of like the opposite, right? It just works. Um, the one thing that you have to be careful about is the distribution of your data. Like you mentioned, if all your vectors are positive, then BQ will just turn it all into a long string of ones, and then nothing is distinguishable from other objects.
Yeah.
That's the one thing that you have. That's the one thing that it cares about, and it doesn't care about other things. But one thing that is interesting about BQ is that up until now we've been talking about BQ, where the model itself that was trained to generate the embeddings had no idea that these vectors eventually were going to be BQ'd and then used in vector search. The people from Cohere, um, and Niels mentioned this on a Twitter thread, a lot of their vectors now that they're generating with Cohere embed v3, they're quantization aware, right? So when you train the neural network to generate these embeddings, you train it with loss functions that know that these vectors are eventually going to be turned into binary versions of those vectors, or scalar quantized version of those vectors. We haven't even talked about scalar quantization, but they know about these quantization techniques, and so they kind of distribute information, knowing that eventually the person that's going to use these will quantize these in this fashion. And so I better kind of distribute my information so that when the squishing happens, I don't lose too much information, which is amazing because when you do BQ on these Cohere vectors, the recall only goes down by 5%. So you go from full recall to 95% of the recall, and you squish the size massively. Right? It's a 32x squishing in size for 5%. So we talked about this kind of, you want the trade-off in memory footprint and recall to be disproportional, and that is disproportional, right? So that's kind of amazing.
Yeah, there's some super smart folk working on this stuff. That's really cool. Just by the way, Zen, every time you mention loss function from now on, I would prefer if you said brownie points.
Brownie, yeah, that's good. That's good.
just, it just makes them even more human, as if we
Yeah.
were doing that. It's kind of cool. Then I guess so those two are the ones that we have implemented already in Weaviate. So those are available to the users already. And
Yeah.
there's like these other new and exciting ones that you've spoken to Abdel about, and Etienne's spoken about them a little bit at his recent talk as well. I'd love to hear you, explain those a little bit more to me, because I don't feel like I've understood those all that well yet.
Yeah. So for scalar quantization, it basically says, look at BQ. BQ is this really kind of radical kind of loss of information where you say, just throw out the number, just look at the sign, right? Is it positive or negative? That's all I care about. So floating point says, okay, let's not go that crazy. We're not there yet. What we're going to do is, instead of taking a number and representing it with like 2 million different points of accuracy, kind of having a huge range of different accuracies to represent that dimension with, we're going to only use 256 different kind of discrete steps, right? So if I tell you that you have to count from 0 to 1, and you can have like 200 steps, however many kind of gradations you want between 0 and 1, if I give you a million steps, you'll be able to kind of take really small steps toward from 0 to 1, right? Now if I tell you only have 200 steps to do this, now you have to take bigger steps, right? And it's easier to lose information now because you don't have the memory or the accuracy to kind of go deeper and deeper into each dimension. So what scalar quantization says is, we're just going to reduce the amount of memory that is allocated. So we're going to look at every dimension, and instead of having 2 million, 4 million different kind of steps on this ladder to represent that dimension with, we're only going to give you 256. Right? And so you squish per dimension that way. And then going back to the what we were talking about with Llama 3 and Llama 2, if the model is these are embedding models now, but if the model is really using all that precision and all that information for every dimension, and you say you're not allowed to use it anymore, you've only got 250 odd kind of numbers to represent each dimension with, well, then you're going to kind of really mess the model up, right? Which is what I think. There's no study on this, but people were talking about how with Llama 3, a 70 billion model performing really well is probably using a lot more of all that precision that's afforded to every weight. And now when you remove that, it's lost a lot of that kind kind of space to store useful information. Whereas the older Llama 2 model had 70 billion parameters, but it really wasn't using all of the different precision that every weight was giving it. So even if you quantize it, you didn't notice that much of a kind of a loss of how well the model performs. I think embedding models work the same way, where if you have a really kind of precise embedding model that's been fine tuned, and then you quantize it, and it doesn't know, it's not quantization aware, it doesn't know about quantization, um, then it'll perform a lot worse.
Yeah, I guess just because you're saving information or data at a higher precision, it doesn't mean you're making good use of it, right? Like
Yeah.
when we've all done things in programming, when you're using some hugely inefficient data structure for like, and then you're like, oh, I just needed to say like binary true or false or whatever. So this is like the opposite of that, how well you make use of that information. And you mentioned saving each dimension as they say one of 256 uh, numbers. So I guess that fits nicely into that's 8 bits. So going from like a floating point number, which is 4 bytes or 32 bits, you're saving three quarters of you're reducing three quarters of the space that's needed. That's pretty neat if you can do that.
Yeah, exactly. And I think some of the benchmarks that Etienne ran, the recall goes from it's about 95% recall when you do scalar quantization, just squish from 32 bits to 8 bits, um, which is pretty good, right? Because 32 bits to 1 bit with BQ is kind of radical, and then you say, okay, maybe if BQ isn't working and you try BQ, the next step would be maybe just squishing it down to 8 bits with scalar quantization. um, and then you mentioned the other two techniques. The other of those two is the one that Etienne mentioned, which is locally adaptive quantization, which is super interesting, right? Basically, what locally adaptive quantization says is instead of so in BQ, we use the zero step, the zero threshold, as a kind of distinguishing factor of, do we want this dimension to be positive, 1, or 0, uh, negative, right? Um, where locally adaptive quantization comes in, and it says each each dimension is going to have its own mean and variance, right? So the first dimension will have a different mean and different variance, and the second dimension might have its own mean and variance. So the you don't just kind of squish the representations equally for every single dimension. You locally adapt the squishing to accommodate where this dimension likes to live, right? If the numbers in this dimension like to live up here between a range of 2 to 5, you don't just squish it based on all the average of where all the numbers in every dimension like to live, right? You kind of look at where this dimension likes to live, and you locally adapt the squishing to where the numbers of this dimension are. And if the numbers of this other dimension like to live down here from -2 to -10, then you squish them, respecting the fact that they're down here, right? And so yet now you're locally adapting the quantization to the mean and the variance of these numbers. And that is, when you account for that, requires a little bit more kind of implementation on the algorithm side, but the recall is much higher. I think it was like 98 or 99%. And we can probably share some of these numbers with folks afterwards.
Oh yeah,
But
that'd be cool.
yeah,
And that's kind of cool. To me, it reminds me a lot of like we talk about traditional machine learning every so often and sound like old people. But one of the classic pre-processing step is centering the data.
exactly.
This sounds very similar. Is
Yeah.
that fair?
Yeah. So, like whenever you do this min-max scalar or normalization, you're
Hmm.
really, if you look into the formula, that the formula takes into account where the mean is and what the variance is, right? Or if you do like min max, you look at where the min and the max of every dimension is, and then you squish accordingly. This is very similar. You pay respect to where the mean or the variance or the min max of every dimension is, and then you adapt the squishing to be kind of the most informative in that location. And this makes a lot of sense, right? Because you don't want the range to be down here when you're only using the upper bound of this range,
Yeah.
and that's you're wasting this whole portion. You'd rather that range be adapted to every single dimension, and this shows up in the increased recall. So it's pretty amazing.
Yeah. I don't know if you used to watch like the show called 24, and the classic thing was like they'd have some blurry image. It's like a old spy show,
Uh-huh.
and the spy guy would always be like, "Can you just zoom in and enhance on that?" and this, and you
Yeah,
know, that's basically saying all the stuff I care about is in these like this
exactly.
region of the data. So you're
Yeah,
saying, can you zoom in there and scale it? And then you kind of think the same thing, right? Like the
exactly.
information I have might go across from 0 to 1, but I really care about this area between, say, zero point 0.1 to zero point 0.4.
Yeah,
So let's get that bit, center it, and then expand it. Well, I guess in this case, you might just turn it into binary or what have you. But you're just saying this is the region of the information that I care about. So let's use that.
yeah,
Yeah. So
exactly.
that's really cool. And um, I guess that would this process be less sensitive to how the model's trained, perhaps,
Yeah, this is an
compared?
interesting question. Yeah, so we talked about BQ requiring the embeddings to be kind of normally distributed. They shouldn't all be positive or negative. You should probably have a good kind of balance between positive and negative dimensions. This one, because the quantization algorithm is taking into account where numbers in every dimension like to live, then the model doesn't have to kind of constrain where they live beforehand, right? So this LAQ technique, I think, is more open. There's not that many kind of constraints that you have to impose on your embedding model in order for it to work.
I guess one thing that also occurs to me on the flip side is that it might be more susceptible to like drift, or if you're training LAQ on a particular data set that you have, and let's say your embeddings are all like, I don't know, medical literature, and then you apply this, and then you later on go and import a bunch of I don't know, um, like vet. I guess vet's probably more like, let's say, I don't know, astrophysics literature.
Yeah,
um, then the LAQ might sort of have applied a certain set of learnings from the medical literature
yeah.
that perhaps won't translate so well to the other corpus.
Yeah, exactly. So it's very similar to PQ in that regard, right? I think it depends on the underlying distribution of the data, and this because it's taking into account the underlying distribution of the data by looking at every dimension. It gets a higher recall, but the price you pay for that is when the distribution just does drift, like you mentioned. You kind of have to refit this. You have to recalculate where these dimensions are, which is the same thing that you have to do with PQ, anyways. Because if the if when you calculated PQ centroids, your data looked one way, and now you've imported 10 million other vectors and now your data looks completely different and you're using those old centroids, then it's not going to be very good. Or you kind of have to refit as the data drifts. You have to kind of quantize. You have to adapt the quantization. That's a good point.
Yeah, I think it's really cool technique. I'm looking forward to trying it out as well.
Yeah,
In some senses, I wonder if it would be one of those things where you just, as a user, just set it up and then it's good to go with default parameters. I assume it'll be somewhat configurable too, but yeah, it'll be cool.
yeah.
Any do you have any ideas of like roughly when we might be starting to see this in Weaviate? Like just quarter kind of, rough timelines. Do you know?
Yeah, I'm not too sure, but I think it'll be the second quarter. Is that I think that's when they're aiming for it to be second or third quarter maybe. But I know Abdel is working on it right now. So one thing that I'm really looking forward to is once you have all these different quantization techniques, and then you have that kind of overfetching and rescoring adaptive retrieval technique that we talked about, is just picking a data set and then benchmarking all of these so that we can tell users, like, given this data set, you can use these benchmarks and pick and choose which quantization technique will kind of will work the best for you. Uh, Initially, when we had one quantization technique, we just use that one. But now, when you've got this entire zoo, I think it'd be good to benchmark these within Weaviate and say, here, this one works better for this other technique, this other one works better, and give people a way to test for their own data. This is more in line with what we were talking about in the first episode, where we really want people to take their data and say, this is the configuration that works well for my data. Okay, you can trust the initial configurations, but I think if you want to get that incremental performance, you really have to do more experiments with your own data as well.
Yeah, I think that'll be cool, and I'm looking forward to seeing Zen. You watch basketball, like quantization algorithm power rankings of the ones that are available,
Yeah.
and then we can make it. Have a little leaderboard or something. Um, what do you generally recommend users, in terms of quantization algorithms when they get started?
So
Curious.
usually, yeah, you because in Weaviate, if you're applying BQ, we actually normalize the vectors. If they're not normalized, then we normalize them internally before we apply BQ, so that the results aren't completely useless. Um, I would just say use BQ, right? For now, I would say use BQ and then see how that goes. Um, because the initial settings for PQ in Weaviate are good, but because that is so data distribution dependent, um, you can get kind of uh, a really high variance in whether it works really well or really badly, depending on your data distribution. I think BQ is just a safer bet to begin with, right? If you just want to enable quantization, kind of turn a flip and not have to worry about it, I would go with BQ. If you want to squeeze every ounce of kind of memory savings and recall trade-off, then I would go with BQ, and then I would configure it and invest a lot of time in it. Yeah,
Yeah, I think that's good advice. And that's pretty in line with what I typically say as well. BQ is just switch it on, see if it works for you. PQ can perhaps give you a little bit extra, but it's a little bit tricky. And also, you need a training set, right? So
yeah,
it'll kind of only kick in when you get to a certain threshold data set size. So I
yeah,
think it's defaults, 100,000
yeah,
objects.
yeah,
Um,
exactly.
yeah, so then you have to be kind of careful about which 100,000 objects do I load from my data set. So it kind of mirrors my overall distribution. Then now you're getting into like sampling issues and things like that. So I think BQ for sure is a good way to get started, and PQ you can for sure play with. And yeah, I'm looking forward to trying out some scalar quantization and LAQ as well. It's gonna be exciting.
Yeah, it's going to be a lot of fun. I know we were going to talk about horizontal scaling, but we've talked for almost an hour on this. So maybe the third episode can be about horizontal scaling. And then I really want to learn about that because I haven't learned about like all the database engineering side of things, the sharding and the kind of no downtime upgrade stuff. I know you've been working a lot on that, learning about that. So maybe we can do that next time. Right? How does that
That
sound?
sounds great. Yeah. As a bit of a preview, I think for me, what's been really cool is learning about how sharding works. And because that's such a good way of, we're talking about scaling databases or our deployed database and just being able to add additional nodes to your cluster as you grow. And then dealing with the problem of, well, as you add nodes or as nodes get removed, conversely, what happens to your data? How do you make sure different nodes or individual nodes get reasonable distribution of your data? So you don't get two nodes with more data than a third node, and how do you make sure certain consistent distribution of different amounts of data as you add more objects, right? So if you add a bunch of objects that start with A, they don't all end up
Yeah,
in node 8 or something like that, or node 1. So problems like that are really cool. And yeah, as you mentioned, the problem of like replication and um, doing upgrades, rolling updates and things like that is really cool. And that would also tie in well with our new version of Weaviate that's coming out next week, which is the 1.2.5 release. That'll have a new consensus algorithm called Raft built in to deal with our schema management. So yeah, that's all really exciting, and that I've been kind of having a good time reading about it. one thing I'll say to people if they're interested in this sort of stuff is that Raft was only, I think, about is about, I want to say, 10-ish years old as an algorithm, and the people who came up with it have this great talk that they're from, I think they're from Stanford, and they give this great talk about how their main goal, I mean, I'm sure the guy's being extremely humble, was that this previous very popular consensus algorithm was very, very difficult to understand. And their goal was, they say, to come up with an algorithm that they could understand, which is, um, you know, people don't say that very often about
Yeah.
algorithms. It's like, I didn't understand this previous thing. It worked,
Yeah.
and there was proof that it worked, but we couldn't understand it, so we didn't want to implement this thing that we didn't understand. So they came up with it, and the video where he talks about it is a really good watch, and the paper is such a nice paper to read because it doesn't go out of its way to be very dense, which
Ah,
I must admit some papers I find a little bit denser
yeah.
than they perhaps have to be.
That's interesting. So I don't know about that talk or that paper, and I'm sure listeners would also like to kind of have access to that. Maybe in our video we can post it, and you can also send it to me afterwards.
Sounds
Uh,
good. Yeah, I'll post it in the comments or something, or
yeah,
description.
yeah, sounds good. Sounds good. Yeah, so I
Fabulous.
think I'd love to, because I have no idea about this. I haven't studied up on it or anything. So I'm gonna come into the next episode just with a laundry list of questions, and then you can just explain everything to me, right? I don't have to watch the talk. You could just describe it to me.
I'll do my best. But yeah, it's a really cool topic, and distributed systems. It's like a whole different field that I'm just like learning just a tiny bit about, so I can at least talk about it without embarrassing myself too much. And I have to say shout out to Etienne and his videos online because they're so good,
Yeah,
and his internal videos that he does as well. So if people are online, I'll post some of those links on our video description as well, because I just get so much out of watching and rewatching some of his videos because yeah, he's, he's the man basically.
yeah. Those videos are amazing. I know the exact ones that you're talking about, and I just binge watched them one night. I was like, oh, there's this whole list of videos on uh, distributed systems, and let's
Yeah.
just watch how this stuff works in Weaviate. And then I've like rewatched them 3 times over now, each one, and just the the way he explains concepts are is really amazing.
Yeah, I know. We need to clone him.
Yeah, we need to have more Etienne's. Etienne, if you're watching
Exactly.
this, maybe I could have like a hair or something.
um, cool. On that note, maybe we could wrap up.
All right. So JP, did you want to talk about some resources where people could learn more about the stuff that we're talking about here?
Oh gosh, thanks, Sam. Thanks for the shout out. So one resource would be Weaviate Academy, which maybe I can go back to if you can. Oh no,
Yep.
that's
Let
not the right
me.
screen. Cool. Yeah, if you can share my screen back up. So if you go to our lovely website, which is weaviate.io, and then go in the developers and learn with Academy. There's a bunch of things in there we've been adding to the library as we go. But the topic that you might be interested in is this section called vector compression. So we talk about P cube or product quantization. We talk a little bit about binary quantization as well, and just some tips about how to go about choosing a compression strategy for you. So that's a good place to get started. We, of course, have the official documentation on the topic as well. So on the concepts, we talk about vector quantization. So that's another resource. And of course, this is a really good topic, and I would also recommend the Hugging Face article on
Yeah.
quantization. I think they've got a blog from a few weeks ago,
Yeah.
and that one was really good as well.
Yeah.
So I would really highly recommend that.
Yeah. That was awesome.
Yeah, so that's what I've got in mind. I don't know if you have anything else in mind, Zed.
No, I think that's everything. Let's wrap this one up, and looking forward to next time learning about distributed systems.
Fabulous. Thanks, Zed.
Thanks, everybody. Have a
Cheers.
great day. Bye bye.